After that, we set the model in evaluation mode. This mode deactivates certain components like batch normalization and dropout features and ensures the model is ready for evaluation. This does not introduce any new randomness or changes in the model behavior. Here, no-grad is a context manager. It prevents model from recomputing the gradients and storing them. Next, we pass this X-test input features and evaluate this predicted values of test data. And then we evaluate this loss for the test data. Then we are printing the training and testing loss that is evaluated in each epoch. Here, generally we use large number of epochs of the order of 10,000, 1 lakh, etc. So printing all the information in each and every epoch basically increases the runtime. Hence, in this tutorial, I am just printing the loss information for every 1000 epoch. So whenever it reached 1000 epoch, 1000, 2000, etc., it will print the loss values obtained in training and testing. Next, after defining the functions for training and testing, we actually need to call them. But for this, we need to set some parameters such as number of epochs, learning rate, model to be used, etc. These parameters are also called as hyperparameters. We have to set these values, and these values control the learning process and effectiveness of the learned model parameters such as weights and biases. We have to do some trial and error to find reliable hyperparameter values that yield the best results for a specific problem and data set. So currently I'm giving 10,000 number of epochs and learning rate of 0.0001, and we have 8 input features and only one output feature, and I'm using this model with more hidden layers. Here you can also use a model with one hidden layer, and you can compare the results that are obtained from both the models. And then I'm calling the train test model that we defined here, and I'm passing all the arguments, the model, xtrain data, ytrain data, xtest, ytest data, num epochs, and learning rates that I specified here to this function. And basically this function does the machine learning for us, and whenever 1000 iterations are reached, it prints the loss information in training and testing. If you observe in the first 1000th epoch, the training loss is 1580.31 and the testing loss is 1575.07. The weights and biases used in the first epoch are randomly initialized, and then using the backpropagation technique, it updates these assumed weights and biases based on the final gradients evaluated at the end of each epoch, and these new set of weights and biases will be used in the next iteration. Likewise, the weights and biases obtained at the end of ith iteration will be used in the next I plus 1th iteration. So, and this is a continuous process. If you notice here, after 1000th iteration, we have got 64.09 training loss, and testing loss is 75.55, and at the 2000th iteration, it is 38 and 3029. At the end of 9000th iteration, our values are very low. Training loss is 15.48 and testing loss is 31.19. It's very good model, I would say. That's it. Once we complete the specified number of epochs that results in low training and testing loss, we can use the model for future prediction on new data by passing the new data to the model. Here I'm passing the testing data that we splitted before just to see how well our predictions are matching with the actual values. Overall, comparing the predicted and original values of concrete compressive strength against the cement quantity and blast furnace slag BFG, the results are fairly good. Our predictions are matching well with the actual values. Let's plot the concrete compressive strength values against other input features. So if you look at here, these two we have seen before, and this one fly ash, water, super plasticizer versus concrete strength, coarse aggregate versus concrete strength, and then fine aggregate versus concrete strength, age versus concrete strength. Overall, predictions are fairly decent, but generally, by looking at these plots, we cannot make any conclusions. We have to have some concrete numbers to make any decisions. So, for that, we are using this R2 square value to evaluate the efficiency of the model. So here, if we evaluate the R2 score between the y-test and y-test predict, we have got 0.87. It means overall 87% of all the patterns that are existed in the data are captured by the neural network, and the remaining 13% are excluded. The R2 value of 0.87 is good. Any value greater than 0.85 is always good. If you have got any value less than 0.85, try rerunning the model until you get R2 value greater than 0.85. This is one simple measure. In our future tutorials, we will learn more about other metrics to evaluate the machine learning model's performance. Let's save the developed model using torch.save. In this new notebook called predict, I'm going to load the model that we saved before, and I'm going to use it for future predictions. I'm loading the necessary libraries and also loading the model that we saved before using torch.load, and I'm creating a new data point where 500 represents the cement quantity, 100 represents the blast furnace slag value, remaining values represent super plasticizer, coarse aggregate, fine aggregate, water, age, etc. I'm converting this numpy array to a torch tensor, and then I'm predicting the concrete compressive strength value. So the model that we developed in this tutorial was able to give 65.58 MPa. So overall 65 MPa. This is okay because our R2 value is 0.87. So we can trust this value. That's it. This is how we develop a machine learning model to predict the concrete compressive strength using PyTorch machine learning library. If you have any questions or suggestions, we recommend you to please write them in the comment section below the video. We greatly appreciate your feedback, and we will do our best to respond to each and every comment. If you like our content, please hit the like button and subscribe to our channel. Happy learning. Thank you.